All right, I think we're ready. We're going to basically just review everything today that we've been doing. So, exam one is coming up, I think it's Thursday. And so we've covered all the content that will be on exam one. Wednesday, I'm not sure exactly what time we'll meet on Wednesday, but the Wednesday content is a couple of things. One, it's quiz 2, I think, is open. I need to actually make that open. Quiz 2 will open, and we'll talk about frames and machines, which are not on exam 1. Quiz 2 would be in the same format as quiz 1, maybe a different number of questions or whatever, but same idea. I do need to, let's see, it's probably not closing on the right time. It is open, apparently, the 24th. That's actually a good time for it to be due. So let me make sure it doesn't have a password on it. Because if it does, then I need to get rid of that. Let's see. It does not have a password. So you should just be able to take quiz 2, and it will give you another little bit of practice. I would do the same thing that I did with the quiz 1, where treat it like the exam. It's going to be simpler versions of the questions. It won't be like the hard ones or everything. Some of these tile from quiz 1 and quiz 2 will be on the style, not necessarily the same problem, but the style of problem will be on exam 1. Exam 1 will be made of some simple problems, some medium problems, and a handful of what I think are harder problems. And generally what harder means is that there's more steps to them. So simple are kind of like one equation, sigma equals force over area kind of thing. Medium ones might incorporate a couple. You got to draw a correct free body diagram and then solve it, something, I don't know. And then the harder ones you might have several things going on at once that you have to simultaneously solve. Or maybe you've got to solve one equation to input it into another equation, something like that. But that's on class 10, so that'll actually be Thursday. So today we'll go over all the stuff from basically classes 1 through 7, or at least as much of the stuff as we can. Now, if there are particular things that you want, I'm not looking at Discord right now because it's kind of hard to keep everything going at once. I'll open it and I can watch it. I probably will miss stuff over there, but if there's a particular thing you want, put it in this chat and I will eventually see it, and hopefully I can do that. My plan is to go to web work over here and work through some of the optional problems. But if there are particular ones that y'all want to see, then let me know, and I'll work through some of those. But we've got 38. I'm not going to work all 38. There are 38 problems in the optional ones. These are all problems from the book that have been turned into web work problems. So there's also a book problem that matches one of each of these. It's just going to have different numbers. All right, so that's my plan. I think we'll just start at problem 1 and kind of make sure we know how to do all of these. Oh, can you explain how the online layout will be? Oh, I'm going to have to write all of that out. But yeah, so because there's going to be options, right? Some people, this is a question asking about exam 1. Some people will take the exam during class time. So that's the ideal situation. We all get on Zoom. I'm on Zoom. You're on Zoom. You log into Moodle, and let's look at it. Exam 1. It'll show up. Well, this is an old one. You could look at this exam 1 info. It's still relevant. It's just an older one. But this will open. And I probably should close that so you can't actually see it right now, because I don't know what would happen if you try to take it early. Probably not good things. So exam 1 2022 will open, and you'll have all the exam right here in Moodle. So that's the ideal situation. You'll finish your exam. There are some of these that might earn partial credit. Some of them are really straightforward and there's really no partial credit available to them. But some of them have multiple parts where you can earn some partial credit. And some of these questions might ask you to draw a particular thing, like the stress-strain plot with the ultimate strength and yield strength and all that kind of stuff. So you will also, once you're done taking the exam, you'll just take some pictures with your phone is fine of the written work that you did, and you'll upload that here in case I want to see any kind of partial credit options. There are a couple of reference materials. One of the things you asked was reference material. These PDFs right here are exam references, so it's all this stuff. Most of this we don't need in exam 1 because these references are for exam 1, 2, and 3. So you might need this page right here. So is this rotate? Yeah, rotate the wrong way. But see, here's your material properties. So you can get your material properties you might need. You can use that exam reference. Exam reference 2 is the same thing, just different set of stuff. It has the centroids in there probably somewhere. There they are. So if you don't remember a centroid equation, they're all in there. But don't be worried that a lot of this doesn't make sense. It's for later. So that's the reference material. Exam 1 reference, exam 2 reference. I do have, let's see what I put in here. This is practice for exam 1. I'm currently, just so you know, I'm currently on class 10, the actual exam class. Usually there's some old practice exams. Yeah, these are retired problems. And so if you want to see some old problems, not going to necessarily repeat these problems, but you can kind of see what some of the older, now these are from 2006, 2007. I don't know how old this one is. Let's see what it looks like. 2009. So these are older test questions, but you can get an idea of the kinds of things that will be on an exam. These aren't necessarily complete exams. They're just pieces of exams. So you can practice with those also if you want some more practice problems. I don't know that those have answers. Some might not. This is just reminding you that this optional 1 that we're going to work on today is going to give you extra practice for exam 1. Challenge 1 also does that, but it also gives you extra credit for homework. You can also have a calculator, obviously. But other than that, you'll have your calculator, exam 1 reference here, exam 2 reference, and you'll have the exam, and that's pretty much all you'll have. Paper to write on. And then you'll have your phone ready to take pictures. So that's the ideal situation. Some people can't take the exam during that time, or that day even, maybe. Maybe they have internship and they can't skip lunch time to do that exam. So in that case, those people, we have to set up a proctor of some sort. So you can get exams proctored at libraries, at other institutions. Maybe you're near a different university somewhere. Maybe you're near tech, but you can't do the exam that day. You could get the proctored there, possibly. Usually the library at tech will proctor exams. Although we have a new librarian, I think, so I don't know what the new rules are. But even public libraries will proctor exams, usually. There are centers that proctor exams, like Sylvan, stuff like that. Some of these you have to pay, some of them are free. Depends on what you have. Maybe you're working under a person who has a PE. They can proctor exam if they want to. So there's a lot of different situations if you're not going to be able to take the exam from 12 to 2 on Thursday. So if you're in one of those situations, you've got to send me an email or Discord message or something so that I will help you figure out what your proctoring looks like. Oh yes, Claire asked, the exam is on Thursday. Yes, exam is on Thursday, assuming you're able to meet. Now, there were a couple of people, actually that might have been one of them, who needed it on a different day. That's okay because there was a school conflict, and that's fine. So we can move some things around if you're in one of those situations where you just can't meet the time that we're meeting. That's the whole point of this course being online, is that a lot of you are off doing internships or all kinds of different things, and we have to be a little bit flexible on when you actually take the exam. So if you're not taking the exam Thursday 12 to 1:50, then I need to know so that we can figure out when you are taking the exam and how you're going to take it. Are you going to get a proctor somewhere? Because I'll have to send them the exam. They got to make copies and all that kind of stuff, and they'll have to send it back to me, all that kind of stuff. So if you're one of the people who's not taking it on Thursday in Zoom with me, then let me know so that we can set that up. if you're fine, you know, this is a good time. Thursday, basically, you'll just log into Zoom and Moodle, and we'll sit there and we'll take the exam wherever you're at. So that's the general idea. I'll write that up because there's probably pieces that you want to repeat, or you can watch this again. All right, I don't see any other questions, so we'll go ahead with some of these. I don't know if I want to solve this one. I will say that there are problems that are this simple on the exam, maybe one that's a problem like this. So this one is not necessarily an equilibrium problem. It's just finding the resultant of two force vectors. And so you might have to do that. You might even have one that's find the x component of a vector or something like that. So these kind of problems are on there. You upload your answers while on Zoom on the exam. What you do is the exam's in Moodle, so you'll actually take the exam like the quizzes, like quiz 1 and quiz 2. It'll look a lot like those, and so you'll put your answers in there. It will actually score the exam, and then I may have to go back and override some of what Moodle scored, because Moodle may or may not have gotten it right, particularly if it's something you type in an answer. Moodle probably is not going to get that right. But yeah, you'll upload, you'll do basically a quiz. Exam 1 is basically a really big quiz in Moodle. And then your paper written work, you'll take pictures of, and you'll upload pictures of your written work, just so I have anything I need for partial credit, because you can't put that into Moodle very easily. So after the exam is done, you'll take pictures of all your written work, upload those pictures into, where'd it go? Into this little spot right here, exam 1 work. So that's what that is. Let's find a better problem than this one to work. Okay, this one might work. Let's do this one. I'm just going to copy the whole thing. Go over to, not MathCAD, we'll go over to OneNote. So this is exam 1 review. That's what we're doing here. All right. Let's see, y'all can not see that. There we go. All right, so we've got this little collar. It says lightweight collar here, meaning that we don't have to worry about the weight of the collar itself. Some situations that might be important, but lightweight is our key word that we can ignore the weight of it. It is free to slide on this rod BC. What that's telling us, the free part, means that we don't have to worry about friction between the collar at A and rod BC. Determine the forces exerted on the collar by the cable, so the cable is labeled cable, and by the rod if the force of this red arrow is 720 pounds, alpha is 17 degrees, and beta is 29 degrees. All right, so what we want to do with this is let's go down here and draw us a little free body diagram. Actually, we'll draw it on top of here, and then we'll copy it down. So we're basically wanting to worry about this little, what they call it, collar. And I'm just going to kind of draw the collar. And then the collar has this force F, which is 725 pounds for me. It has a force from the cable here. We don't know that one, so it's just F cable. I'll probably call it FC in the end. We have a couple of angles here that we can, let's put a coordinate system right here at our origin. This one's a concurrent force system, so that's usually the best place to put. In fact, there was already an X and Y axis there. X, Y. We've got this angle alpha for me is 17 degrees. It's all getting cluttery, but we're going to move it in a second. Beta is 29 degrees. And the force between the collar. So the collar here, you have to kind of figure out what this collar doing. It says it's free to slide, so there's no force in direction BC. but collars, we haven't really talked about those, I don't believe. We talked about pins, we talked about rollers, but collars are a lot like rollers. So the idea is that they constrain motion in one direction. So it's free to move in direction BC along this rod, but it's not free to move perpendicular to that. So when it means it's not free to move in one direction, that means there's something resisting that movement. So there's some kind of normal force here. We'll call it Fn. So some kind of normal force inside the collar that's between the collar and the rod. We don't know what it is. In fact, it's called force from the rod, so we don't know what that equals. Let's put us another little line up here. I notice I've got to put that line. And so that's going to actually do more like that. All right, let's see if we can copy all of that little stuff and lost it. Move it down here. All right, so there's our little free body diagram that we're dealing with. We have two unknown forces. I've got them kind of going in the same direction here, so that's not going to work. Something's going to have to give. Maybe I could go ahead and fix that and move Fn to where it points up and to the left. That might be a good thing to do since it's obvious it can't go this way. If it's not obvious it can't go that way, that's fine. You just leave it that way. When you solve it, you'll just get a negative number and know that, oh, I drew that arrow the wrong way. Now I've got something that pretty much looks like any other 2D concurrent force system that I've already solved. So Fn is kind of unlabeled, but I do know it's the normal force between the collar and the rod. Normal meaning perpendicular, so I do know that this little guy is a 90-degree angle. So I know that this angle is 29 degrees, right? Just based on the rod is rotated 29 degrees, so perpendicular to that has to be rotated 29 degrees also. Now I've got a simple setup where I can write some equilibrium equations. This is 2D concurrent forces, so I only have two equations, x and y. Both my unknowns have unknown values in x and y, so I'm going to have to write both equations and solve them simultaneously. For exam 1, I would expect that you're going to need to solve something simultaneously, either one of these 2D systems or one of the 3D systems, or both. So you do need to have a way. You're not going to have MathCAD, even though you're on your computer. You only have Moodle. So you're not going to have MathCAD. And so you got to use your calculator. So make sure you know a effective way to use your calculator to solve systems of at least 3 unknowns. So because there's probably a 3D concurrent force system on this exam 1. And there'll certainly be a 2D one, if not a 3D one. But I would expect to have a 3D one. All right, so what this says is the force in the cable times only the x component of it, so cosine 17 degrees minus the force, the normal force between the collar and the rod, times the sine of 29 degrees equals 0. I can't solve that equation. Has two unknowns, but I can write another equation in the y direction because I have two equilibrium equations. I know this collar isn't moving in x or y. It's not translating in either of those, so these two directions have to add to 0. X has to add to 0, and y has to add to 0. I'm going to write them in the same order just to make it line up. So negative force in the cable, because it's pointing a little bit down, so it has a negative y component, times sine of 17 degrees plus, because the normal component I drew, when I redrew it, I drew it going up and to the left, cosine 29 degrees minus my 725 pounds equals 0. Probably be a good thing to move that 725 to the other side of the equal sign. What I'm going to do is I'm going to copy this little guy right here. I'm going to go over to MathCAD. We're in MathCAD. Paste it. It's going to be gigantic. We'll make it a little smaller. And we'll just throw this in a solve block and solve it over here. Again, not what you can do on the exam 1, but you can do it other times. I'm going to call this force cable equals 1 pound and force in. I'm not using subscripts. It's just so that's a lowercase n. Our constraints are that force of the cable times cosine of 17. Got to tell MathCAD that it's degrees. Minus Fn times sine 29 degrees. Control equals all of this thing. Control equals, to do a symbolic equals equation, 0 equals 0. I probably need to put 0 pound force on that. I'm not certain about that. We'll see. Negative F cable times, I didn't put a, oh no, I think I did. It just simplified it. Sine of 17 degrees plus Fn times, times the cosine of 29 degrees. All of that. When I move the 725, it'll become positive pound force. Find F cable and F cable and Fn. Uh-oh. What did I do wrong? Can I not do both of them at the same time? Maybe when I hit the why are we having trouble? I just want to find F cable. Oh. Do I have to do it this way? Answer 1 equals find F cable. Nope. What am I doing? I did Fn. I did those as symbolic equals. Did that. That's the problem. Why do I have extra parentheses around these, I wonder? Keep typing it as a lowercase. Huh. Not sure why it doesn't want to solve these. No solution was found. All right. Maybe it wanted to find both of them at the same time. I don't know. But I wanted in pounds. Let's see. So apparently F cable is 505.985 and F in 998075. Let's see. Let's slide that over so I can see both of them at the same time. All right, so the rod is for me, and the cable. It's always, a little scary. Oh, we got them right. All right. So that could be. I could definitely see this problem being something you would do as a medium level one. It's not like a one-liner. You've got a simultaneous set of equations. You got to draw this free body diagram. You got to think through. So this would be more of a medium level problem, not one of the easy ones. But I could see this being a thing you could do on the exam as one of the actually a little bit tough problems because of the simultaneous equations you have to do. There's not another way to do it. And it takes a little bit of time to set up the equation, check it, do it, get it right. So I could see this one being on the exam, but one of the not hard problems, but upper level problems. Something that separates maybe a B from a C. Maybe not one that separates an A from a B, but maybe separates a B from a C. Something like that. Let's find another one to work. That's just more of the same type of stuff. That's also more. This is a silent. This one is probably actually a really pretty tough one. If I put something like this, where you've got to make two separate free body diagrams, connect them together, kind of like those two squirrels on the rope, that would be almost a hard problem. But we're not gonna think about that one. This one is. It looks like it's 3D, so it looks hard, but it's actually really straightforward. The one thing on this one is that it's drawn with the origin down here at the ground level, right? But the concurrent location is up here at point D. So this one works much easier. It is lengthy because, you got to write your all your little cosines. You got to figure out all your little cosine angles. But if you move this origin up to D, this one becomes pretty straightforward. It's just lengthy. And that's probably kind of the thing you can expect on the exam is if there's a 3D concurrent force system, it's not that they're complicated, it's just that they're lengthy. And so they do count as one of the harder problems just for the length that they are. This would be a good one to work through. It says the same thing. The origin is over here, but the concurrent point is at A. So this would be another one. If we have time at the end, we'll come back and do one of these, but they're a small portion of the exam, so I don't want to take a bunch of our time here just doing these. But if there's time at the end, then we'll go back and do this, but they're a pretty relatively small portion of the exam. So let's find, all right, this one's a good one. Let's copy this guy. And let's go to here. All right, so here now we're in the mechanics type of stuff. This other stuff, this is all statics, right? So now this is in the mechanics stuff. I've got two strips of plastic material, so are bonded together as shown. So the two strips they're talking about are, this piece and this piece, and they're bonded together with these top and bottom. Maybe those are pieces of tape. They're just really thick, drawn pieces of tape. The average shear stress in the glue. So the glue is on these pieces of tape. I'll try and draw it, but it's kind of on the top side. It's right here and right here. So there's glue in those green spaces between the top and the two little yellow plates. And there's also on the bottom, but I can't draw that without just coloring over where I already colored. But the shear stress in the glue is limited to 990 kilopascals. So that's your shear strength for this glue. What length L of a splice plate, so the splice plates are the two little plates on top and bottom, the ones in the middle. How much is needed if the axial load carried by the joint, so that's P, is 55,000 newtons. All right. And the width, they give us the width W as 285 millimeters. This is a pretty good one. This is, I don't think this counts as a super easy one, but it is pretty, it's on the separate a C from a D kind of level. You do not have to draw free body diagrams to get credit unless the problem specifically says draw the free body diagram. It will help you, but it's not going to be graded unless the problem specifically says it's going to be graded. That being said, it's usually best to draw you a diagram because if that problem happens to be one that I'm looking at as partial credit, that free body diagram would be some of that partial credit. So let's say that you don't know how to do the problem at all, but you draw the free body diagram correct, and that's a partial credit problem that I'm looking at. I don't look at every one of them as partial credit. Some of them are too straightforward to really have partial credit. But if I see your work and like, oh, well, he's got the free body diagram correct, just didn't do the math right or didn't set up the equations, then you at least get something for it. So here's what I'm going to do for a free body diagram. I'm going to take the little yellow piece on the right, and I'm just going to draw a side view of it. So let's just do this. Now this is larger than what they've drawn, but whatever. Here is the 55,000 newtons. And then on the top surface, I've got a shear stress here. I guess this is a shear force. And a shear force here. These have to add together to balance out our 55,000 newtons. So basically, I'm assuming, which is what we're going to do in this course, is this kind of assumption. I'm assuming that the 55,000 newtons evenly spreads across the top and bottom. So this is 27.5 kilonewtons with the other 27.5 kilonewtons down here. So now the thing is balanced, and this dimension, how am I going to draw that? We'll draw it like this. That dimension is what they have. Actually, that's L over 2, right? Because they do show this little gap right here. We're assuming that gap is 0. It doesn't give us any information about that gap. It's just there for, I don't know, just to make the picture look more clear that there's two separate yellow pieces. So since it doesn't give us a dimension for that gap, we're going to assume it's basically 0. All right. And then into the screen here, we've got 285 millimeters. Now this problem specifically tells us the average shearing stress. So we do know it's a shear just based on the problem statement. Not every problem is going to tell you normal stress, shear stress. You know, it's not going to always give you that clue in the problem statement. This one does. But make sure you know that you can look at a picture like this and tell that that's a shear stress versus a normal stress. And you tell by looking at the force that you're dealing with in your stress equation and the area that force acts on. If the force and area are perpendicular, then it's a normal stress because they're normal to one another. If they are not perpendicular, if they're parallel, is how they're going to be in our pictures here. If they're parallel, the force and the area that force acts on, then it's a shear stress. So I've got tau, that's a shear stress, equals V, shear force, over the area the shear force acts on. They limit tau in the problem statement to 990,000 pascals. So I'm going to do it this way, so I don't get mixed up on my thousands somewhere. I'll do it this way. Although I guess my forces are in thousands of newtons also, so we probably could drop it off and it'd be fine. The shear force, the total shear force, is 55,000 newtons. That's 27.5 on top, 27.5 on bottom. Add those together, 55,000 newtons. The area that those two shear forces act on, there's two of them, one on top and one on bottom, so 2. And they have a width of L over 2 and a thickness into the screen of 0.285 meters. So I converted everything over to, my base units. You don't have to do that, but if you might get confused, you might be off by a factor of 10 or 100 or 1,000 if you don't convert them all to the same correct units, and you're not careful about that. So I just convert them all to the base units. All right, let's see if we can make this solve here. L is what we want to solve for. Well, let's see if MathCAD can do that. I don't know. All right, so we'll just grab this guy. I wish MathCAD could just take the picture and figure out what I'm asking it, but I don't know that it can do that. But we can put this equation into MathCAD with a symbolic equal sign. Newtons, whoops, over 2 times L over 2 times 0.285 meters. Now, I'm not as good with this version of MathCAD, so we'll have to see. I want to do the solve. Maybe I need to do the whole equation. Well, it won't let me do that. Solve for L. Got a weird number here. Newtons over meter pascals. All right, we have to figure out if that's the right set of units because that's weird. First of all, did I put everything? These are not the, well, that has units built into it. That's newtons, pascals. All right, so a newton, meter, pascal. Let's see if that's the right units because I want L to be in meters, right? So let's see. What was it? Newton over meter pascal. A pascal is a, remember you calculate Pascal as force over area, so it's a Newton per meter squared. So if I have that plugged into there, then I have a Newton over a meter times a Newton per meter squared. Newtons cancel out, this cancels one of those out, and that turns into meter. So that is the right unit. Not sure why MathCAD thought it was best to put it this way. So 0.19493 meters. Let's find our little deal here. And this guy. All right, 0.1949 meters. It wants it in millimeters, so that's going to be 194.93. 94 for the total L, right? Yes, we got it right. All right, so that's a decent one for a simpler level problem, but not too simple. There's a little bit of figuring out how to go about solve this one, but that would be kind of a design problem even because you're figuring out based on your material strength, the strength of this glue, you're trying to figure out how much glue you need basically. So that's an interesting problem. Let's find us another one. This thing, this one has a lot of good ones. I don't want to work through all of them, but this one, if you kind of want to practice all of your stress stuff at one time, go solve this problem because it's got all of your bearing stress, shear stress, normal stress, tear out stress. They're all in this one problem. So it is a good one to practice. This is optional problem 8. That's a good one. There won't necessarily be, I can't think if there is. I don't think there's a problem on the exam where you have one problem that has like a bunch of answers like this one. It would probably be broken into 4 different problems, but I can't recall if that's true or not on this exam. I'll have to look at it. I haven't looked at it recently. Again, this might be one we come back to, but this would be a good one for you to practice. We basically did this one with the squirrels, right? We should do this one just because it's a different thing. This one counts as one of the pretty straightforward ones, but we haven't done this one or one like this, I don't believe, so we'll do one. Also, by the way, this one? Yeah. Where's today? Exam 1 review. I did an exam review last year where I did the same kind of thing, and I might have picked out different problems. So you can go to look at this one and see what problems I did back there, and it might give you even some more review. I might have picked some of the same problems, though. I don't know. I surely don't pick them all exactly the same. All right, so this one is a shear strain problem. So I've got the rubber mounts. The rubber mounts are the pink parts on this picture. They're used to isolate vibrational motion. Now, we're not worried so much at like frequency of motion and all that kind of stuff in this part. We're just thinking of the shear strain. So it, meaning the pink block here, has dimensions L equals 1/2 inch, W, which is labeled, equals 2 inches, and into the screen, it's 4, so it's really long into the screen. Determine the average shear strain in the rubber mounts if the rigid frame displaces that far, 13,000ths of an inch, vertically, relative to the support. So what this means is I have got, here's my little pink block. I don't have a pink color in here, I don't believe. I don't even know how to add a color. Whoops. Oh, wait, look, there's pink right there. How do I add it? I want to use that pen. All right, so this guy is the pink block. I guess pink, so it can look like a rubbery material of some sort. There it is. And it would have probably been better to draw a rectangle on top of that, but not a pink rectangle. There we go. There's our little rubber block. Now, it is attached to where it doesn't move to a wall over here. So this side doesn't move. But the left-hand side of this thing is attached to this little upside down U-shaped bracket, and it moves up and down. But in our case here, we're looking at like one instance in time where it's pushed down. So instead of this shape, let's draw another one. Where are those little pink? There we go. I don't know if I'll get this one very well, but this is the second state for it. It's kind of like this. And we'll try and do this. I don't know. No real point to. I just want to do it. Oh, it goes that way. All right. Want to. Why can I not? There it goes. Oh, it doesn't let me skew it much. Oh, well, that's no good. We'll just draw it by hand. So it skews over like this. And this part is still attached to the wall. So the shear strain is that angle, gamma. So that's all it's asking you to do, is calculate that angle, gamma. And they tell you in the problem statement that basically this point moved down. For me, it was 0.013 inches. They also tell me that this length is 1/2 inch. They also tell me W, but I don't need W. So to calculate gamma, it's just tangent of gamma equals the opposite side, 0.013 inches, over the adjacent side, 0.5 inches. The inches cancel out, and I just calculate gamma equals... and I can just do this math directly, typically, 0.013, 0.5, so it's just half of that. Or, well, twice of that, I guess, because we're dividing by half. 0.026, no units. So, and if I did the actual tangent alpha of this, you know, calculate that, the tangent of 0.026 is pretty much 0.026. Hopefully we did that right. Yes, we got it right. This one would be one of the simple problems. So all of this drawing and everything, you could quickly sketch that out if you needed to. But all you're trying to do really is calculate, you know, deal with this little triangle or this triangle. It doesn't matter either. They're the same triangle. So you're just trying to figure out the angle gamma right there. So those are really straightforward. And there could be one on the exam one, is possible. But they would be ones I'm expecting you to look at and spend a minute or two on and be done. Oh, this will be a good one to work. Now, this one's got a lot going on, but this probably is worth doing this whole thing. All right. All right, so I've got a collar, two collars on a rigid yokes. Well, the yokes are shown as the little, what I called collars there. They're on this square. Okay, that bar is square, it's not round. 2.2 inch square steel bar. And the forces applied to the bar are all these numbers. Now this one is one of those where you have to look at the forces like P2 and P3, and are they individual forces or are they one force that's distributed? These are showing two separate arrows, so both of those P2s are adding 46 kips to the load. If they were connected together, then that's one force that's distributed a total of 46 kips. So they're not that way though. So these are, let's put our numbers in. We've got 84. These are all kips. I'm gonna leave off the kips because it's gonna get really cluttery. We've got 46 here, another 46 here, 27 and a half here, 27 and a half here, and 47 here. Okay, we have lengths 7 feet. It doesn't give me the thickness of B and C. We're assuming it's negligible, or it's not part of what we're trying to do. It's so much bigger than the square bar that it doesn't really change length much. So B is 5 feet and C is 3.5 feet. And first thing it wants me to do is, what is the maximum stress anywhere in this bar, sigma max? So I've got 3 distinct sections ignoring B and C, ignoring the blocks at B and C. They don't give us any dimensions or materials or anything about those. So we're going to think that they're pretty much not changing length. They're not stretching or compressing. So only section AB, section BC, or section CD of the square bar are what I'm interested in. So let's do this little guy. Cut it open right there. That free body diagram is going to do, well, it's square, but I drew it kind of as a round bar. There's the external 84 kips. So inside that one, there's 84 kips right there. That might be the biggest one. Let's cut open BC. Draw that free body diagram. So I'm going to start at that same location. There's B, which we're kind of ignoring. And then there's where we cut it open. So we've got 84 here, 46 here, and 46 here. Need my calculator. So that's 92 minus 84 is 8. So I need 8 kips going this way to balance that. So I have 92 pushing to the left and 92 pushing to the right. So there's only 8 kips in that section BC. So that's way less than 84. So still AB is our section that has the highest force in it. And then let's do CD. So the easy way to do CD would be to draw the right-hand side, right? Just draw this little piece. And inside there, I've got 47 there, so I must have 47 here. So yes, section AB has the highest force. Does it have the highest stress? In this case, it will, because they all have the same cross-sectional area. Now, if they had different material, well, different sizes, the material doesn't matter for stress, at least as far as we're doing things. if they had different sizes, like section AB was really big compared, like had a big cross section compared to section CD that had a much thinner cross section, then yeah, maybe CD does have a higher stress. But they all have the same. It says, the problem says, well, it says this: fastened to the 2.2 inch square steel bar, AD. So the whole bar is the same size. So we can calculate the stress in section AB equals the force in section AB divided by the area, cross-sectional area of section AB. So the stress equals the force in section AB is this one. I guess I could label this. This is AB, this is BC, this is CD. So the arrow for that one is pointing away from the free body, so it's a tensile force. It's stretching out section AB. I don't think this problem tells us to use positive and negative for compression and tension. Doesn't look like it does, so we're just going to calculate stress. And so 84,000 pounds. The area, it said it was 2.2 inch square. So what that means is that it's 2 inches by 2 inches. It doesn't say, let's see, it says bar. If it said tube, then we'd have to figure out how hollow is it, but bar, rod, stuff like that means it's solid. So this is a 2.2 inch on each side solid piece of metal. So the area is 2.2 inches times 2.2 inches. So that leaves our stress to be calculated. $17,355.4 pounds per square inch, so that's PSI, or 17.35, well, let's do 36 KSI. Let's see if WebWork likes that. Oops, 17.36. I don't know how many decimal. I did round some there, so it may not like it. Nope, it's fine with that. Okay. Now the next little piece. Again, you will have problems like this on the exam. It probably won't be that there are 4 individual questions about one problem. I might give you one picture and then ask individual separate questions about it, so each one can be correct without you having to get the others right, so that they're not cascading with one another. Like you make one mistake in part A, then you automatically miss all the other parts. All right, so delta AB, so that's the change in length of section AB. All right, so delta AB, it is going to matter here if they're positive or negative, because positive is going to mean it's stretching, negative is going to mean it's compressing, getting shorter. So the force in AB times the length of AB divided by the area of AB times the modulus of elasticity of AB. So the force in AB is a positive 84,000 pounds. The length of AB is 7 feet, 12 inches per foot, so that I have inches in that part. This is pounds. The area we just did 2.2 inches times 2.2 inches. That's the area. The modulus of elasticity, sometimes you'll have to go find, these reference sheets. Which one? That one. And look up the modulus of elasticity over here. So it could be that you have to do that. This particular problem, it gives us right here, E equals 30,000 KSI, so 30 million PSI. So all of these units should cancel out except for that inch right there. And we'll have our units in inches. If you forget and don't convert LAB from feet to inches, you're going to get some weird numbers here. So make sure you get your conversions done right. So 84,000 times 7 times 12 divided by 2.2 divided by another 2.2 and divided by 30 million. 049. Positive because the 84,000 pounds was in tension, so it's getting longer. Let's see if, where did Weber go? I think it's right here. Oh, well, all right. So this one you would get right on the exam, but it's actually 04859. I put 049, so doesn't like that. I need more decimals to. So 4859504. Now it's happy. All right. Well, let's go back to here. Delta BC. This one is the change in length of just section BC. So delta BC is the force in BC times the length of BC divided by the cross-sectional area, which is the same, and the E, which is also the same, because it's the same material, same size, so the the denominator doesn't actually change. So the force here, you got to look at that one. That's this force. That arrow is pointing towards my free body, so it's a compressive force. So this is actually minus 8,000 pounds. It was 8 kips. The length of BC, I think, was 5 feet times 12 inches per foot divided by this same stuff. I should have saved that. It was 30. So this one's going to come out negative. It's getting shorter. It's going to be a small number, though, because it's a shorter length and a much smaller force. And let's definitely put more decimals with that one. I think it was 0. That's 0.0330579 inches. See? So we need the negative. And it likes that with that many decimals. The last part here is delta total. So to do that one, I'm not going to do that one. I think we've got the point on this one. We can move on. But to do that one, we would also need to calculate the force, the axial deformation in CD using that 47 tensile force right there. And then add up all of these deltas. So we'd add the 049, the negative 0033, and then whatever we got for CD, add them all together, and that would be the total change in length for the whole piece. All right, so, and there will be something, again, maybe not 4 pieces to one problem, but there will be one of these axial deformation problems on there, for sure. All right, let's see, we've got plenty of time. Let's just make sure there's no questions over here. Nope, don't see any. All right. This is the same type of thing. It does add in a bearing stress. So bearing stress is a normal stress. The only deal with it is the stress, the area, the stressed area in the bearing stress is the area between the two things that are pressing together. So in this case, it would be the bearing stress between the column and the lower bearing plate down here. So it'd be basically the cross-sectional area of the column. So that's pretty straightforward. This one, I could see something like this being on the exam. It would be one of the more simple problems, though. This one's a tricky one. I'm trying to decide. This one's kind of tricky and not really the point. I don't like tricky questions on the exams. That's more for homework, just to work through it. I don't want you to have to learn stuff on the exam. I want you to demonstrate the things you have learned. And so this one is more, it's a good problem, probably not a good exam problem, just because it takes you a decent amount of time to work through all the equations you have to set up to do it. This would be a good one to practice to make sure you really understand the axial deformation stuff. I'm not going to work through it though, because it's not quite representative of a exam problem. This certainly is. There'll be one of these. This one, it also includes a change in length, but this is basically just a straight up 2D concurrent force system. Mass is given in kilograms here, so you do have to convert that over to a weight multiplied by gravity. And then it's actually asking you what diameter these rods need to be. So this is a good one, but it's not a straightforward 2D concurrent force system. I mean, the forces are, but the problem's asking you for kind of a design thing. This is a good one to practice on. That's another axial deformation. Same thing we just did, except now instead of one rod that's all the same material, all the same diameter, this one has two different sections that are different sizes. This one has three different sizes. This one is, I wouldn't worry with this one. This one's good problem, not a test problem. It's kind of like that one that I talked about a few problems ago. This one there might be something. This one's pretty simple, but there could be something like this on the exam. So just in case, let's work through it. That's MathCAD. We don't need MathCAD right now. All right, so all this one's trying to do is get you to calculate moments. So you've got two forces, F1 and F2. So I've seen, sometimes I put a problem like this, there's two forces. Sometimes there's a force and it's at some angle and you figure out the two components to it. But the idea here is that you've got some number of forces and you've got some labeled point. In this case, the point is O, down here. And you want to calculate what moment do these forces create about point O. Now this particular one is asking for two things. It's asking for what moment does the force F1 create about point O, and what moment does the force F2 create about point O. So this problem doesn't say to use clockwise or counterclockwise as positive. So if they don't tell you, it could be, if it's multiple choice, it could be that all the answers and they have CW or CCW on them, or it could just be it wants kind of the magnitude of the moment. So this one would be M1. The force 1 is 8 pounds. L1 is 12 inches. The units are that the problem wants is inch pounds. So M1 equals F1 times L1. So force 1 is a vertical force. I need a horizontal distance between this line of action and point A. That horizontal distance is labeled L1. So in this one, all you have to do is 8 pounds times 12 inches. And that's your answer. M2 has a horizontal line of action. The vertical distance between that horizontal line of action and point O is labeled L2, which is 19 inches. F2 is 26 pounds. And so M2 equals force 2 times L2. Sometimes you have to break forces into X and Y components. In this one, they're just already in X and Y. So 26 pounds times 19 inches. So we should be able to just plug those numbers into. I wonder if I can do 8 pounds times 12 inches. No, it doesn't know that. So it's got to be 8 times 12 inch times pound. well, yeah, it's already has the units. I just need to do 8 times 12 and 26 times 19. That's what it wants. There we go. All right. So there are questions like this one, but typically it's that the force is at some angle, and you want to find the total moment that that angled force creates about some point O. This one's a good one to practice with, but I don't believe there are three-dimensional moments on exam 1. Yeah, this is a good thing to be able to do, but not for exam 1. They just kind of take too long. Same thing with this. This is a centroid by integration. A good thing to know, but they take too long and they're a little bit fiddly if you don't know how to integrate this ellipse, you know. So that's more something that you need to be familiar with, but not for exam 1. We did this one, didn't we? I think we did this, or at least part of this one, so that's not one we need to work. There definitely is a centroid problem on exam 1. Let's do this one. We haven't done this one. Okay. So find the x and y coordinates of the centroid of the shape. Now they have already given me, and this is true for the exam problems, is you already have a reference axis. So you have to work with that one, or at least translate your answers back to that origin. So it looks to me like I've got 1, 2, 3, 4 parts here. 2 negative parts and 2, oh no, I just have 3 parts. 1 solid half circle and a negative triangle and a negative square. So our dimensions, let's go ahead and label those. R is 140. Again, these are all millimeters. I'm going to leave the units off just to save some room. C is 74. A is 80. B is 75, so that's not a square, it's a rectangle. And this particular problem is asking for both X and Y. Probably on the exam, it's just asking for one of those things. So, what I usually do is make my little chart here. I've got part 1 is going to be the half circle. Part 2 is going to be the little negative triangle. Part 3 is going to be a little negative rectangle. I need their area, and it's going to be in millimeters squared. The area of the half circle, I have a radius, so let's do pi r squared divided by 2. Where's pi on here? There it is. Pi. Radius is 140. But we want to divide by 2 because it's only half of 1. That number is huge for millimeters, but I guess we'll go with it. 30,787.608. The triangle is 74 times 75, also divided by 2 because it's a triangle. Don't forget to, but it's negative, so 2,775. And then the rectangle, 80 times 75, and that's just what it is, but it's negative 6,000. So our total area is, we just add all this stuff up. So 30,787.608. Subtract off 2775 and subtract off another 6,000. 22,012.608 millimeters squared. Okay, now let's do y sub c. So I like to go in and mark where I think the centroids of each one of these shapes is going to be. You don't have to do that, it just kind of helps me visualize it. So part 1, the centroid, that one, maybe you don't remember the equation for a centroid location for our half circle. So you got to go to your reference material. Here they are right here. Make sure, let's zoom in. Make sure you're not using the arc. The arc is like a rope or a wire. It's not solid, so make sure you're using the solid, the colored in one. So it says y sub c, that's the distance I need right now, is from the bottom up to the centroid, is 4r over 3 pi. Okay, so 4 times r over 3 times pi. And let's see what that equals. $59. Does that seem? Yeah, it seems reasonable. 59.418. The triangle, that one I do remember, but if you don't remember, where's the triangle? Here it is. From the centroid down to the bottom. Now, sometimes you have to reorient the triangle in particular, but it's basically 1/3 of this longer, or well, of the straight side. So 1/3 of 75 millimeters, so 25 millimeters. The square is right in the middle, so that's just 75, but it's divided by 2, so 37.5. Now, I guess we'll scroll over here. No, let's just drop down. A times y. So our area, 30,787.608 multiplied by 59.418. 1,829,338.092. This is part 1, part 2, part 3. Part 2 is 2775 negative times 25. So negative 69,375. Part 3 is 6,000 times 37.5. Negative 225,000. And then we'll have our summation here is 1,829,338.092. 69,375 subtracted 22,500 subtracted 1,534,963.092 millimeters cubed. And y sub c should be summation of a times y over a total. So I'm not going to write those numbers again. I'm just going to use them. That number, 22,012.608, 69.731 millimeters. Let's look and see if that kind of makes sense. Yeah, it kind of does. You know, I just kind of guessed where to put this thing, and that's more or less where it's that. Well, that's the centroid for the half circle. This is the centroid for the entire thing, which should be even further up. So that kind of makes sense. All right, so let's try 69,731 for y sub c. Now again, web work, you know, oh no, we actually got it right. We were off in the thousandths, 2 10,000ths of a millimeter. To get x, we would do the exact same thing, except we'd have to do the x coordinate. The one tricky thing there is the x coordinate for the triangle is actually negative. The x coordinate for the half circle is 0. And the x coordinate for the square is just 40, so it's really straightforward. So the one tricky part is making sure you put that distance in as a negative 74 over 3, 1/3 of 74. Again, this is another one of those problems where you probably don't have to do X and Y. I just give you a picture and you do one of X or Y, whichever I tell you. Let's see what else we have in here. Oh, distributed loads. We didn't really talk about distributed loads. Let's do this one because we didn't talk about it. It's possible that it's just a centroid, but since you haven't necessarily seen a distributed load very often, or maybe at all, then it would be good to look at this one. All right, so what this is doing is these pink arrow area region things are trying to show you that we mostly, have been doing these point loads, like a 8-pound load that's pulling straight up. But sometimes you have loads that are spread out, and you really can't look at them as a point load, so they're distributed. We have two different types of distributed loads here. We've got this one, which is unevenly distributed. And that could mean a lot of things. In this case, it's kind of just a linear slope going from 0 force, whatever the force is, I don't know, pounds per foot up to 210 pounds per foot. So it just varies between those two. And then obviously the ones that look like rectangles are evenly distributed loads. So what you want to do is sometimes when we're working on problems, particularly stuff we'll do in after exam 1, for solving maybe a moment equation, we want to be able to lump these distributed loads into a single point load. And what I want to do is I want to find where can I put one big point load that has the same effect moment-wise, like it creates the same moment about point A. That one force creates the same moment about point A as all these distributed loads. So that's what this problem is asking you to do. F resultant is just basically calculating the total force. So let's back up a little bit and treat each of these. They are forces, but we're going to treat them like they're just areas, just like this. So this force, or this distributed load, creates some force here. That force is just the area of this triangle. So A is, for me, 5.6 feet. And B, we'll need it in a minute, 2.5 feet. These heights, so the height of the triangle kind of represents the magnitude of it, but they have weird units. So the height of W1 here is 210 pounds per foot. So if we look at just the W1 box, let's just look at just this piece. So just that piece, it is 210 pounds per foot tall, and it's spread over 2.5 feet. So that represents one force that is 210 times 2.5. 525 pounds. Same thing over here, except it's going up, right? So this one, W2, is 30 pounds per foot, but it's spread over 5.6 feet. So it's a total of 168 pounds, pushing up on the beam. The unevenly one, the triangle one, it's the same thing. You just have to remember to calculate the area of the triangle. So the height of this triangle is 210 pounds per foot. It's spread over 5.6 feet, but it is a triangle, so I now have to divide by 2. So 588 pounds. So the total force, F resultant is what they've called it, is 588 plus 525 minus the 168. 945 pounds. So what the X line of action problem part means is, where would I put that 945 pounds to create the same moment as these three separate ones? So this is point A over here. Summation of moments about point A equals, I want to basically make a seesaw, something where all of these individual forces are balanced, or they create the same moment that this 945. So 945 pound times some distance, we'll just call it X, does the same thing moment-wise that 500, I'm doing clockwise moments are positive, by the way, 588 pounds times this moment arm. This one, this is a triangle. I might need to go look at my little reference sheet here. This triangle is shaped the same way as this one, so I don't even have to try and mirror image or anything. So I want the distance from the centroid. That's where, when I was drawing these in the 525 and the 588 and the 168, I put those forces at the centroid of that individual shape. So this 588 is at the centroid of the triangle. So it's X sub C, 2/3 of the base. So this little arrow is 2/3 of the base, of the triangle, which is 5.6 feet. So it's 5.6 times 2 divided by 3. 3.77. No, 3.733 feet. All right. The 525, I'll do this, plus 525 pounds. That one has a moment arm all the way back to A of 5.6 feet plus 2.5 feet divided by 2. So 1.25. So 6.85 feet. Minus, because the 168 arrow is pointing upwards, creating a counterclockwise moment. And that one is just half of 5.6. 2.8. So what this says is that the left-hand side, 945 pounds, which is the entire, all of these distributed loads added together, they would add to a total of 945 pounds times X, is creating the same moment that each individual little distributed load creates, about 0.8. So the only unknown in this equation is X. So I should be able to solve for X if I do all the math here. Let's see. Well, let's make sure the 945 is right. Here. All right, that's right. Now let's make sure that we can figure out where X is. So we have 588 times 3.733. 525 times 6.85, and add that to the previous thing. 168 times 2.8, but subtract it. So the right-hand side, right-hand side is 5,320.854 foot-pounds. So that's the moment created by all the individual arrows that I drew. 945 pounds times X is what I want to create the same moment. So basically I divide this foot-pounds by 945. So 5,320.854 foot-pounds divided by 945 pounds gives me X equals 5.631 feet. So if I went over, well, the way this picture is drawn, if I went over right here and put 945 pounds, that one force, 5.631 feet from point A, creates the same moment as all these little individual distributed loads. And that's, it doesn't bend the beam the same way, but it helps me at the early part of some of the calculations if I can figure out what the net effect of a bunch of distributed loads is and lump that. The word is lump. So lump all those distributed loads into a single point load, and I can do some calculations with that, particularly when I'm doing summation of moments and things like that. 5.631, let's make sure that's right. Yes, it's in feet. Do be aware of the units in the problems on web work, but also on the exam. And that was right. Because sometimes the units might be shown in something that you calculated inches, but the units are feet or whatever. This one, yeah, let's do this one. Do we have time? Yeah, we have time. We don't talk about pulleys very much, but they are a static problem that's pretty straightforward. I guess that's why I don't talk about them, is because they're really pretty straightforward. But a couple of assumptions with pulleys. One is, let's see. Well, this one doesn't actually say that, but it says this, says it right here. Free to rotate. And the rope is continuous over the pulley. So those are two little clues. Free to rotate means that there's no drag on the sheave here. We're also assuming that there's no friction between the rope and the sheave. The sheave is the pulley. The pulley is really like the assembly, and the little wheel looking thing is the sheave. All right, that's just naming stuff. So what that ends up being with the simple pulleys like this is that no friction anywhere, and the rope tension never changes. It changes direction, but not magnitude. So for this one, I've got a 1,175 pound block down here that's being lifted up, and I want to figure out how much tension is in the rope. So what I do is I basically cut through the thing, and let's draw this free body diagram. So I've got the little pulley, got the bigger pulley, I've got some rope. Well, they're connected together, right? They're connected together with a little block. And then the rope goes around everything. So the rope comes off here. It does say, assume all the rope sections are vertical. So even though this one's drawn kind of angled, I'm going to draw it this way. Comes off here. Comes off here. I've got, well, I'm going to put it right here. 1,175 pounds pulling down. I've got tension in the rope here, tension in the rope here, tension in the rope here, and tension in the rope here. So I've got 4 rope tensions all pulling up on this thing. And that I know they're all the same because it's one continuous rope. So it's all the same tension in that rope because there's no friction on the sheave and there's no friction between the rope and the sheave. Now, if there was friction, this wouldn't be exactly true. The tension would gradually decrease as the rope went around more and more sheaves. But we can just write summation of forces in the y direction equals 0, and I've got 4 T's going up, balanced by 1,175 pounds going down. The tension in the rope is just divided by 4. 293.75 pounds tension in the rope. Oh, 7.5. Oops. Correct. All right. So that's, we're not going to have really complicated pulleys, if there's any at all on exam 1. But that's kind of how you deal with them. You just have to make sure that the key is all frictionless, first of all. And then where is this one continuous rope, or are there multiple ropes in there? If it's a continuous rope, that rope has the same tension anywhere you cut it open. And it's all about drawing the free body diagram then. Let's see, we're getting close on time. This is kind of the same thing. This would be a good one to do for calculating reactions. Just what's the reaction at C? That'd be an interesting one. It does have these little issues about being mass of kilograms. The other tricky thing on this problem is that it looks like the center of mass of the beam is right at point B, but that's not necessarily true. B is given by these dimensions, A and B, but the center of mass is just A and B divided by 2. It's right in the middle. And A and B are not the same dimensions, 1.9 and 1.4. So center of mass is not directly under point B, if you want to work with that problem. That's just kind of a tow truck problem. It would be good to work through some truss problems. This is a pretty, obviously there's a lot going on here, but it's a simple truss. There will be at least 2 trusses, maybe more, but at least 2. One that is set up best to work with method of joints, and one that is set up best to work with method of sections. You can use whatever process you want, but there's going to be one that's better for sections, one that's better for joints. And they're not going to say this is the method of joints problem or the method of sections problem. I think we worked through this, or worked through part of this one. These add in the idea that you're also doing stress and change in length in the member after you find the force. So they're combining stress and statics, strength of materials and statics. This is, I'm not going to work this one, but let's do something with this one just to prove a point, I guess. All right, so this is one of the problems that is good to like take a few minutes to kind of plan your solution process. So I've got a 3,000 Newton load right here at some angle 27 degrees. And all members are made of structural steel, so I'd have to go look up their material properties from the little reference material. Determine the change in length in members FG, so this guy, CD, this guy. Oh, that's it. And they give us our cross-sectional area, so we don't even have to calculate it. It's just given. Then it gives a bunch of lengths. So normally what you do with this, you think, oh, it's a truss. I can see that. It's all triangles and everything. There's no forces that are applied directly to the member. They're all at joints. That's all good. I should solve for the reactions at A and B, which is totally fine. But if you look at this one, it's kind of clear that it's setting you up to do a method of section right here, right? You don't need DG necessarily, but you need those other two. And once you look at that, then, well, if that's what I'm trying to do, then I could just skip all the reaction stuff and draw this free body diagram. Put my 3,000 newtons over here. Put the force here, and force here. I've got 3 unknowns. I've got FG, DG, and CD, along with my 3,000 newtons. And I don't need any of the reactions at A or B because I'm just using the section that's at the top. Also, this is a zero force member if I needed to know that. That doesn't necessarily help me, but with the doesn't help with the problem it's being asked, but that is a zero force member. So at that point, you could go in and you could do summation of moments about D, and you'd find out FG, and then you could do summation of moments about G, and find out CD and do the rest of the problem. So that one, I'm not going to solve it, but that one is a good one to kind of see where you don't always have to follow the cookbook of draw the free body diagram, find the external reactions, and so forth and so on. This one, I guess you could go that route. It's just going to take much, much longer to do it that route. And you've got to deal with these weird angles here that aren't given. You've kind of got some dimensions. You could calculate them, I guess, but you don't need to do all that. Let's see what else. This one's definitely set up for method of sections. So this sign probably has a weight. It weighs 3,270 pounds. So when you have something like that, and it doesn't specifically say that the sign is some weird shape, you know, it's just a rectangle, then what you do is you take the 3,270 pounds and divide it evenly among all of the little cables holding it up. So 1,090 pounds on each cable. That's a little more complicated of a problem. I don't think, yeah, that one is kind of like maybe the very first problem we solved with the adhesive, or one of the earlier problems, the shear stress on the adhesive. This one's the same idea, but now the glue is in a cylinder shape, so it's different cross section or different area. This is a decent one for calculating shear stress or in a pin with 1, 2, 3, 4 quadruple shear. That's the same problem. I guess it's just asking for a different answer. Again, same thing, asking for shear. Different. They're the same one, but asking for different things. There's another. This is actually an old test question, I believe. Same thing. That's an old test question that is just a truss problem. That one's more about drawing a good free body diagram. It's a little bit complicated. You've got the one thing over here with the roller not on a flat surface. The roller's on an incline. So the reaction at this roller is perpendicular to that incline. So you do have to catch that a little bit. That's probably a little beyond what we were going to do on the exam. These last few, well, that one wouldn't be bad to work through, I guess. Oh, actually, let me look at it. This joint H is kind of troublesome, but this is a zero force member, and you've got some weird stuff over here. So that one might be a little, I don't know if I would work that one for an exam problem. It's a little bit more involved. If you want to do some practice exam trusses, these, wherever they are, this one's good, that one's good, and that one's good, and that one's good. All right. I think we're close enough to out of time that we wouldn't be able to do a whole nother thing. On Wednesday, we won't have class at the normal time. I don't know what we will do. I'll let you know when I get closer to Wednesday. I just won't be here to do the exam. Oh, not the exam. Do the class at 12. But I will, or I did already, open up quiz 2. I would go ahead and do quiz 2 because it relates to exam 1. And then the frames and machines stuff, that is a new topic for exam 2. So we will cover that. I just don't know exactly when. It'll be later. Or we might just use this video because it's already done. If you want to watch at noon, like that's your normal time, just go ahead and watch this video and I'll do a different one. Just it won't be at noon. And then on exam 1, Thursday, let me know if you are not planning to take the exam on Moodle at the regular class time on Thursday, because I gotta know who your proctor is and how you're going to do all that. All right, I will see you guys on, well, sometime on Wednesday, but I'm not sure exactly when. I'll see you on Thursday for sure, or whenever you do your exam. All right, see y'all later.